Dr. Patrick Whippey, and he's a professor of physics and astronomy at Western University in London, Ontario. And Dr. Whippey, live on the call with us, we have our camp in Dundas. So Dundas can give a wave. Hi, Dundas. There's Dundas. And we also have Sudbury with us as well. So hello, Sudbury. Hi. And we also have our camps across Ontario watching the live stream of this call too, and they're submitting their questions on Twitter, and we already have some good ones coming in, so it'll be a good question and answer session today. So as you may know, today is Energy Day at STEM Camp, and the campers will be learning about things like the transfer of momentum, friction, potential energy, kinetic energy, as they build their Rube Goldberg machines. So I know the campers have many questions about energy and things that will help them design and build their Rube Goldberg machines. But first, Dr. Whippey, can you tell us a bit more about what you do at Western University? Also, I understand that you have some experience building Rube Goldberg machines, perhaps, so maybe you could tell us a bit more about that as well.
Well, yes, I'm actually retired from Western now, so I'm no longer an active teacher. I did my PhD at the University of Reading in England, studying diamonds, actually, using a technique that's pretty much disappeared now. You don't hear much of it, called electron spin resonance. And then I moved to Canada and have taught physics at the University of Western Ontario for about 43 years. And now I finally hung up the chalk and dusted off the blackboard for the last time. So, and then in my retirement, I'm continuing something I started actually at the beginning of my Western career, which is to organize and run science fairs and science Olympics competitions. And in the Science Olympics competitions, one of our big events is the Rube Goldberg event. And that's an event for high schools. And so these Rube Goldberg events tend to be fairly big machines. In fact, we say it's got to fit now within a 4x8 foot area, because that's only the space we have. That's, oh gosh, in meters, about 1.5 by about 2.5 to 3 meters, and essentially the size of a large table. And they get very elaborate. Oh, I see people jumping up and down and waving. Hello, it's great to see you. And as part of the training for that, I have something I call a Rube Goldberg kit, and I do little workshops on that. And in this kit, and it's all inside one Ziploc bag, and everything's bought from the dollar store. And there are things like marbles and rulers and pencils and string and balloons and dominoes. And we also give you a couple of big rulers. And your job is to do the most complicated, simplest task, and do it in the most complicated way possible. Because Rube Goldberg, in fact, was a cartoonist. He worked in New York for in the 20s, and he became famous for some of his cartoons, which indeed take the simplest possible task and do it in the most complicated way possible. So you're following in that great tradition.
Great. So maybe I'll go to Dundas. Do you have a question about Rube Goldberg's machines or how you could design one?
We have a question about energy. Nobody's got a question exactly about Rube Goldberg right now. Oh, is that all right?
Yep. Oh, yeah.
Okay.
Is light matter?
Sorry?
Is light matter?
Is light matter? Well, light is energy. It's a form of energy. The simple answer is yes. Because light is a form of energy. It's actually what's called an electromagnetic wave. And the light that we see with our eyes, in fact, is a very tiny fraction of all electromagnetic waves, because the only thing that varies from one electromagnetic wave to the other is the wavelength. And at very long wavelengths, we call those radio waves. And at the absolute other end of the spectrum, radio waves can be the order of meters or tens of meters long, or even kilometers long. At the other end, At the tiniest scale, like 10 to the minus 16th of a meter, we call those gamma rays. And they're generated, they're very high energy and come in outer space. Now, energy, of course, is connected to math through that most famous equation of all in physics, E equals mc squared. So, because light has energy, it's also a form of matter. So they are, yes.
Oh, that was a good question to lead off with. How about in Sudbury? Is there another question?
Yes, there is. Okay.
Great.
Just looking to the screen. So
How does energy transfer from thing to thing?
I'm sorry, could you get a bit nearer to the microphone and speak up just a little bit? I couldn't pick that up.
How does energy transfer from thing to thing?
How did it transfer from
thing to thing.
thing to thing? Well, energy actually is a very subtle idea. We know how to measure it in some cases. We can see it in some cases. I mean, I can see in front of the table on you a bag of some sort. Can't see quite what it is, but there's a bag there. Now, if you lift it up, can you lift it up? That's it. That's right. Now, you've increased its energy. You've increased its potential energy. Now, we're not going to do this for real, but if you dropped it, but don't, if you did drop it, it would start to move downwards, and it would be moving. And moving stuff has another kind of energy called kinetic energy. So you can make energy change from one form to another just by letting nature do things. You know, if you just take that piece of paper that's on the table and just let it drop onto the floor, it's starting off with a potential, and then as it drops, it's losing potential and gaining kinetic. The problem with energy is it's in fact a very difficult thing to get your mind round. You know, it's like many things in physics. We teach it to grade 3 students and say, well, it's actually very easy. Well, actually, it isn't. I don't know whether you have time, but Richard Feynman had a very elegant picture of energy. He said, look, imagine that here's Feynman's picture of energy. He said, okay, imagine that there's George. Now, George is 2. And when you're 2, you like rituals. And George had blocks. And George wouldn't go to bed until he'd found all his blocks. And so his mother was counting up the blocks on Monday, and she found 14 of them. And that was great. And then on Tuesday, she could only find 13. And then she had to hunt round, and she found one under the sofa, and then all was well, George would go to bed. So, you know, on Tuesday, it was all the blocks she could see plus the one under the sofa. Well, on Wednesday, George had his bath, and he put some of the blocks in the bath, and he wouldn't let his mother get them. And so she was kind of stuck. But she discovered and realized that she measured the height of the increase in the bath, and she was able to figure out that in the bath, there were, by just measuring the increase in the height of the water, there were in fact 3 blocks in the bath. So the 11 she could find plus the 3 in the bath, that was 14 blocks. All was well, George went to bed. And so it goes. And so what she had was a bunch of formulae that at the end of the day, you add up and you always get the same number. And that's what we find with energy, is you find a formula for energy, and then you add up the formulas, and if you do it right, you always get the same answer. Now, so what you do is you put the block on the on the table, and you find it has a certain amount of potential energy, and then you knock it off, and if you measure it very carefully, and you measure the speed just before it hits the floor, you find it's got some kinetic energy, and the two are the same. And the analogy with the blocks is this, is that as each day, Mum would find some formulae, and it always added up to 14. And it's the same with energy. And the only difference is there aren't any blocks. Energy is a very abstract idea that turns out to be super uber useful. But what physicists have done is to figure out all the different formulae for energy, and when you add them up, they always get the same answer. But what that means is energy is kind of an abstract idea.
Okay, so
I can see the kids are quite young, and so that's kind of a somewhat more advanced and maybe not mean a whole lot to the to some of you. But gradually over time, if you remember this story and come back to it when you're grade 9 or 10, it'll make more sense at that point. But yeah, the energy is abstract, hard to get your mind around.
Yeah, there's a question from our camp in Ingersoll that might put it in more real terms, perhaps. Since energy can't be destroyed, where would the energy go if we threw a watermelon off of a tall building?
Well, eventually all energy ends up as essentially as random motion that we often call heat. And so when you throw the melon off the building, it hits the floor. Now, a number of things happen at that point. First, the melon breaks, and then you get water and bits of metal all over the lawn, and the groundskeeper gets mad because he's got to go and pick them up again, unless you're tidy and pick it up yourself. Do that. Good to be tidy. And so the water splashes around. Eventually, when it hits the ground, it skids a bit, so it loses a bit of energy to friction, so it warms up the grass just an eensy-weensy bit. As the melon is falling from the building, it's pushing air out of the way. That speeds the air up and warms up the air just a teeny-weeny bit. It makes noise. Sound is a form of energy, and sound energy eventually dissipates and gets so small you can't hear it anymore. But then again, all it's done is essentially make the atoms in the air move just a little bit more, and we call that heat. So energy eventually all dissipates. It ends up as thermal energy, but that effect is that thermal energy, since it's dissipated amongst the essentially all in the air, we don't notice it, and so it looks as though the energy has disappeared, but it hasn't really. Not if you keep track of it. But keeping track of all the bits of energy, when a melon falls and splays into 1,000 pieces, that's kind of hard to track. So there we are.
Okay, so there's another question from our camp in Tilsonburg as well as Brantford. They want to know, where does energy come from and how is energy formed? That might be a very difficult question as well.
Oh, well, no, that question's easy. The answer is I don't know. Okay. It is part of the universe that was given to us. It's just here. And one of the great mysteries is how did things get going in the first place? And because a lot of our energy on Earth comes from the sun. And what is the sun? The sun is just a very, very large hydrogen bomb. Fortunately, it is 93 million miles. I'm sorry, what's that in meters? Can't do it in meters. I grew up in miles, you see, and so those numbers are stuck in my head. But the sun's a long way away, and it is just a hydrogen bomb. Now, where does it get its energy from? Well, the sun has hydrogen and another isotope called deuterium in it, and if you heat up hydrogen and deuterium to a very, really super high temperature, then you can get two hydrogen molecules, atoms rather, to come to two protons to come together. And when they fuse, you have a little bit less mass from the combination than you do in the two originals. So it's like throwing two billiard balls together and then finding out that when you threw them together, you had a little bit mass less when they fused together than when they were separate. And through E equals mc squared, that little bit of loss of mass shows up as energy. And that's what keeps the sun going. And that energy turns into electromagnetic energy that then travels through space, and a small fraction of it hits the Earth. And that's where a lot of our energy comes from.
Okay, good question, Tilsonburg and Brantford. Let's go back to Dundas. Dundas for our next question. Yeah.
Hello, Dundas.
Hi, I've got a question here. Devin's just on his way up. We've got a big room here. So he's making his way over.
Hi, Devin.
Hello,
Here's
Devin. Hi.
How can we use energy?
How can we use it?
Yes.
Okay, how can we use energy? Well, if we didn't use energy, we probably all wouldn't be here. We're using energy when we do anything we do. When we get in the car, and when you got in the car, when you ate breakfast this morning, you were changing the energy from the energy stored in the Wheaties to a form that your body can use. So that's one kind of energy. And then you got in the car, and you used energy to travel all the way from your home to the school or the center where you're having this wonderful workshop. And every time you move your arms around, you're using energy. Anytime you see something, you're using energy, because light is a form of energy. So energy is all around you, but because you can't see it, you don't think about it, and you only learn about it when you go to school and take a great physics class. Of course, you're all going to go to school and take physics classes, aren't you?
I think so. All right. How about in Sudbury? Is there a question in Sudbury?
Go ahead, Nim. Just look down here.
What's the most important thing to think about when you're building a Rube Goldberg?
What's the most important thing to think about when you're using a Rube Goldberg? Oh, well, I don't think there is a most important thing. Now, I don't see on the tables the stuff that you're going to use to build your Rube Goldberg stuff, so I'm not quite sure what you're going to be using. But what you've got to do is use all the apparatus that your workshop leader has given you, and use those to build ramps. They're a great thing to build. Sometimes if you've got string, you can climb up and hang the string through the little beams on the ceiling and build a pendulum. I see a kit there. Oh, wonderful! And the teacher's getting out the kit. That's great. Oh, a tennis ball. Okay, so we've got tennis balls, we've got balloons, we've got popsicle sticks, and one of the great things. Oh, and clothespins or clothes pegs. Absolutely. Aha! And here's more things. Oh, and toy cars. This looks suspiciously like the kits that I have. So I wonder whether somebody found my and cards. I think you have found my list of things for the Rube Goldberg kit, because there they all are. And so what you've got to do is to use the marbles. And of course, when the marbles roll, they have kinetic energy. And when you have dominoes, and you can have great fun with dominoes. Oh, by the way, there's a trick with dominoes. If you set them up so that they all fall down, then when you're setting it up, you want to leave a couple of spots in the middle and leave a couple of dominoes out, because it's very easy to just jog the dominoes when you're lining them up and accidentally knock them over before you're ready. And that creates great consternation when your machine is almost ready to go. And of course, you can, if you say you've got string, you can make a pendulum. One of the fascinating things, and I've been doing this for a long time, is that every time I do a Rube Goldberg kit, it doesn't matter whether it's grade 3 or grade 12 or teachers, because I do it with teachers as well, someone comes up with something I've never seen before. It's quite extraordinary. And so one of the would be interesting to see if you can come up with something that I haven't seen before. And so I hope you'll be able to do that. And you probably will, because you can use the little bits in the kit that you've got in a whole variety of different ways, and each class comes up with something different. So I don't think there's a most important thing. I think the trick with Rube Goldberg's is can you master the effects of friction, which get in the way and slow things down. And so you find when your car, instead of going straight, it goes slightly sideways. It's kind of controlling all that sort of stuff that turns out to be hard.
Wow, yeah, I'm really looking forward to seeing what all the campers can come up with this afternoon. I hope you share some pictures or videos later on this afternoon, because I'd love to see them. And Dr. Whippey, I think you would too. We could even share them with you later on as well.
Yeah, if you fix a time, I'll log on. Or maybe you can.
Okay.
I'll be home. If you got my home phone number, maybe you can phone me at home and just say get on the machine, and we're ready to go.
Okay. Okay, that's awesome. So that's all the time we have for our call with Dr. Whippey today. Thank you very much, Dr. Whippey, for answering all the questions about energy and Rube Goldberg machines. And thank you, Dundas and Sudbury, for joining us live and asking all your questions as well, and all our camps across Ontario who submitted questions on Twitter. So thanks, everyone.
Okay. Bye-bye.
Have a good day.